A heavy metallic projectile fights the immediate crushing force of gravity the exact moment it clears the launch tube. The height of that flight path over time is represented by this specific quadratic function, h of t equals 96t minus 16t squared. To determine the success of a mission, engineers have to answer a specific question. Is it physically possible for this projectile to reach a target height of 160 feet? To find the answer, the physical scenario is translated into a standard quadratic equation, 16t squared minus 96t plus 160 equals 0. Finding the value for t usually involves traditional classroom methods, like factoring or applying the full quadratic formula. But calculating the exact time points is often unnecessary when you only need to know if the target is reachable at all. There is a mathematical shortcut that can test the limits of this flight path before you commit to the full calculation. This shortcut is built into the quadratic formula, a mathematical method with deep historical roots found in the work of ancient Indian and Persian mathematicians like Sridhara Acharya. If we focus strictly on the internal core of that formula, we find a specific expression, b squared minus 4ac. We call this the discriminant. It functions as a diagnostic tool that identifies the nature of the roots, telling us what kind of solutions to expect without solving for the exact time. The discriminant's value reveals which of three possible mathematical outcomes applies to the physical system. If the discriminant is greater than 0, the parabola and target line intersect at two distinct points, once on the way up and once down. If the discriminant equals 0, there's exactly one solution at the absolute peak. If it's less than 0, there are no real roots. The intersection never happens. Let's apply that b squared minus 4ac calculation to our projectile's 160-foot target. The calculation results in a negative value under the square root. Because the roots are complex, the projectile can never physically reach 160 feet. As this handwritten graph clearly shows, the actual physical ceiling for this launch is 144 feet, reached at exactly 3 seconds. By identifying that the discriminant was negative, we proved that the experiment was doomed by the laws of gravity before ever leaving the ground. This same logic applies to other branches of physics, including the behavior of electrical circuits. Take this system, a 100-watt lamp and a 20-ohm resistor connected to a 120-volt power supply. Running the quadratic formula here results in a positive discriminant, providing two separate valid operational states, 1 amp or 5 amps of current. While quadratic equations process variables with perfect logic, they lack the context of the physical environment. As this engineering note points out, equations can produce answers that are mathematically sound but physically impossible, such as negative time or negative resistance. At this point, the human observer must act as the final filter, identifying and discarding results that violate the known laws of nature. Quadratic equations provide a reliable framework for testing physical boundaries on paper. From the early derivations of Indian mathematicians to the modern classroom, analyzing the true nature of roots allows us to understand the practical limits of the world around us. For the Explainer, created with education.